Okay, we're going to make a couple of statements. First, different parameterizations of the same curve with equal parameter intervals give us different portraits of our changing tangent lines. So that if we have the same curve with three different parameterizations, so that, for example, this curve would be maybe r of t. This curve would be r of, don't want to use x, let's use, don't want to use s because that's distance, and I should have thought this out, not getting hung up on just what to call this parameter. R of, okay, say W. It's first letter I can think of that doesn't have another connotation. And now I've got to think of a third one. Let this be R of, I'm going to use S. Why not? Okay, if I let t change by equal time interval, by equal t intervals, and we could think of this as time if we like. You know, our unit tangent vectors might be here, here. As thing speeds up here, similar to what we saw before. And our changes in the unit tangent vectors would probably look something like this, and maybe so. W, whatever W is, we might have a completely different portrait. At this point, our unit tangent vector might be here. Now at some interval W, we might jump all the way from here to here. And then in an equal W increment, we might only move from here to here. That's going to give us a much different change, a much different portrait of how our tangent vectors, our unit tangent vectors, are changing. Now if we do R of S, and I'll let S be the distance increment, in which case I'm going to have to draw these at equal distance intervals along the curve, then it doesn't matter what R of t looks like or R of w. On this one, we are going to have a decent indication. Actually, we get the definition of how the unit tangent vector changes with respect to how far we've moved, and this is going to be a picture that gives us our curvature. And this picture is going to be the same no matter whether the curve is originally parameterized in terms of t or w. Once we get down to parameterizing the curve in terms of distance along the curve, the picture is going to be the same no matter what we started with. Okay, now equal intervals of arc length then give us a portrait that actually indicates average curvatures. And we're going to define then curvature to be the rate of change of the unit tangent vector with respect to arc distance, because of course it's arc distance that we're measuring when we measure the distance that we've traveled along the curve. So we're going to divide the change in t by the change in arc distance, and that's going to be a derivative of t with respect to s, where s is arc, I don't want to say arc distance, I want to say arc position, and a distance being a change between two arc positions.